Hi folks, we are continuing on with day 11 in the Unit 3. This video is looking at the distance from a point to a plane. This is a very similar proof, and I'm not going to actually go through it all in the video. It's very similar to the point to a line in R2, just kind of extrapolated into 3 dimensions. We're still going to be using the normal vector, which is now going to be ABC from the Cartesian equation of our plane. If you want to take a look at the full proof, that's on page 542. But I'm just going to, at this point, give you guys the equation for that because it is very similar to what we did in the first video. And you come up with quite a similar equation, again, using the idea that this distance from a point to the plane, which you can kind of see in blue, this blue parallelogram here, that this distance over this vector magnitude would be cos theta, kind of rearranging that dot product and then using the dot product of these points and the equation of the plane. You do, just as a kind of note here, you need to have the equation of your plane in Cartesian form. If you're given it in vector or parametric form, you're going to have to convert that into Cartesian. It only works with the Cartesian equation of a plane. So we're just going to do a quick example of this one. And we're going to find the distance from this point to our given plane. So the equation for distance is the magnitude of A x naught plus B y naught plus C z naught plus D, so this absolute value, because we only want a positive value, divided by the magnitude of the normal, which is the square root of A squared plus B squared plus C squared. So you can see the similarities there with the distance from a point to a line in R2. So we know that my normal, the normal vector here, which is ABC, is 4, -2, -1 from the coefficients of the x, y, and z, and that this is x naught, y naught, and z naught as the point that you're finding the distance to. So again, pretty straightforward if you know the equation. This is the absolute value of basically subbing this point into the line, or into the plane's equation. So we get 4 times -2 minus 2 times 1 minus 5 plus 6, and take the absolute value of that. If it's negative, we'll change it to positive, divided by the magnitude of this normal. So 4 squared plus -2 squared plus -1 squared. So on top we've got absolute value of -8 minus 2 minus 5 plus 6, so that'll be negative for sure. And then the square root, 16 plus 4 is 20, plus 1 is 21. So here we've got -10, -15, and then up to -9, but we do need to make this positive because distance is a positive number. So we take the absolute value, 9 over root 21. And again, you can rationalize the denominator or change it to a decimal as appropriate. Okay, one last example, and I'm going to kind of combine these last two topics, is the distance between skew lines. I'm going to use a method, and there's a few different methods here that you can use, but I like looking at this as the dot product. So skew lines, remember, are lines that are not parallel and do not cross. If you have two lines that are parallel, you can just find the distance from any point, so the position vector of 1, to the second line, because the distance will be constant all the time. So maybe I'll make a note of that so you guys will see it in the notes as well. So with parallel lines, the distance is constant you can find distance from any point on first line to the second line. So if you were given two lines that were parallel and you wanted to find the distance between those, it really goes back to being the distance between a point and a line. And you just take the position vector of one line and find the distance from that point to the other line. Okay. With skew lines, though, this is where we're looking at two lines that are not crossing, so they don't touch, but they're not parallel. So they will have a shortest distance, and that shortest distance, let's see if I can kind of show this a little bit better. The shortest distance is going to happen when that distance between them is perpendicular to both of the two lines. So what we're going to do, we're going to say that there must be a point on one line and a point on the other line where that distance happens. And we will know that the vector between those 2 points is perpendicular to the vector along one line and also perpendicular to the vector along the other line. So I'm going to say P1 on line 1. So this general point on this line will be 1 plus 2s for the x value, 5 minus s for the y value, and 3 plus s for the z value. And then we're going to have point 2 on line 2. That point will be 0 plus t, or just t, 5, oh, no t's there, that's going to make this easier, negative 2 minus 5t. Okay, now we know that the vector between these will be perpendicular to this direction vector and this direction vector. So I'm going to find vector P1, P2. And this you need to be pretty careful with, like not mixing up negatives, being really careful with your calculation. So I'm doing the end minus the start. So I have t minus 2s minus 1. And then I have 5 minus 5 plus s because it's minus negative s. And then I have negative 2 minus 5t minus 3 minus s. So then I'm going to simplify this up a little bit. T minus 2s minus 1 is done. 5 minus 5, that's kind of nice. I just get an s for my y component. Then I have negative 2 minus 3. So this is going to be negative 5 minus 5t minus s. So this is vector between the points P1 and P2, and we're going to say this vector is where it's perpendicular to both lines. So if this is perpendicular to both, then P1, P2 dot M1, or the direction vector of line 1, will equal 0, and P1, P2 dot M2 will also equal 0. So this isn't something you need a formula for. You just have to really understand the relationships between these. Sometimes people get mixed up with, like, is this a point or is it a vector? Why do I have to subtract them? So kind of really thinking visually about what this means. So you've got this line here and this other line here, and they don't cross, and I'm drawing this way too big. And there's some point here, P2 and P1. So you want to kind of define those points and then get this vector between them so that the dot product, this vector is going to be perpendicular to both the direction vectors along those two lines. And again, it's very hard to draw realistically in 2 dimensions something that is 3-dimensional. But if we have this, and we also know that the dot product of this vector with the 2 others is 0, we can come up with some equations. So I'm going to do that. So this might get a little bit messy, but we can do it. So I'm going to say P1, P2 dot M1 equals 0. So I'm going to use this as M1 and then M2 just from the second line, the direction vectors there. So P1, P2 is T minus 2S minus 1, S negative 5 minus 5T minus S. And I'm going to do the dot product of that with 2, negative 1, 1. And I know that it has to equal 0 because it's going to be perpendicular. So just doing some algebra here with the dot product. So I have 2t minus 4s minus 2 minus s minus 5 minus 5t minus s equals 0. Looking at my t's, I get negative 3t minus 4s minus another s is negative 5s, negative 6s. And then the number parts, I had a minus 2 and a minus 5, so they'll go to the other side and be 7. I'm going to do that same thing with the second one. And here, I'll use P1, P2 dot M2 equals 0. This one is pretty involved to be able to find the distance between skew lines, but the process is just kind of hopefully pretty intuitive if you understand the relationship between those. So then I'll do the dot product of 1, 0, negative 5 equals 0. So I get 1 times this one plus 0 times s minus 5 times this stuff. So t minus 2s minus 1 plus 25 plus 25t plus 5s equals 0. And then how many t's? I get 26t plus 3s equals, this would be 24 and negative 24 if I bring it to the other side. So I am going to need more paper in here. I've come up with 2 equations, both with variables for t and s, and we'll just solve that with substitution or elimination. So I'm going to have to go on to another page here, and I'm just going to copy out those equations. So negative 3t minus 6s equals 7, and 26t plus 3s equals negative 24. I'm going to do elimination and multiply this one by 2. So negative 3t minus 6s equals 7, and 52t plus 6s equals negative 48. Adding down to eliminate these, I get 49t equals negative 41. Oh dear. T equals negative 41 over 49. And then I'm going to sub that in to either one of these equations. I'll just use the first one, negative 3 times negative 41 over 49 minus 6s equals 7. So that's 123 over 49 minus, bringing the 7 over, and the 6s to the other side. It is getting pretty messy here. And I'm going to divide that 6 negative 220 over 294. So this is a super messy situation. But so if I haven't made a mistake, it is pretty messy, and it is really actually unusual for it to be not messy. But we can take this S and T value, and we know that P1, P2, so once you figure out those two, so this vector, your distance, is the magnitude of P1, P2. So P1, P2 is going to be, do this up here. So P1, P2 is T minus 2S minus 1, and then S, and then negative 5 minus 5T minus S. So I'm just going to throw this big mess into a calculator and figure out what the components of P1, P2 are. So negative 41 over 49 minus 2 times this big mess minus 1. So this is negative 50 over 147. This is just S, so negative 220 over 294. And then this will be negative 10 over 147. So I think this is actually 110 over 147 there. And then the magnitude here will be the square root of all of this stuff. So negative 50 over 147 squared plus negative 110 over 147 squared plus negative 10 over 147 squared. So real life numbers are not often pretty. So 50 squared plus 110 squared plus 100. So here we get square root of 14,700 over 147. And I don't think that that reduces. This guy might change into a mixed radical in a little bit lower form. But that's the process. I do have kind of a list here of how to go about this. So taking this out, finding the distance between skew lines, there are a few different ways of doing it. I like this process because it makes the most intuitive sense to me. So you're going to get general points P1 and P2 on the lines. You're going to find the vector P1, P2 and dot product with both direction vectors. Make it equal to 0 because it's perpendicular. Use your two equations that you come up with to find S and T, and then use S and T to find the magnitude of that shortest vector. So find the points, P1, P2, find the vector, and then the magnitude. So going through that process, that is what we're going to do to find skew lines. There are a few other solutions to that. I think that one is posted in your outline from the CEMC, and there's also a different alternate method to do that in your textbook. And that wraps up everything we're going to do with vectors. We're at the end of Unit 3 and moving on to calculus in Unit 4.